A 30 cm long European-sized 2x4 can carry more than 2300 kilos or about 5,000 pounds of concentrated load. Of course, this number becomes much smaller for longer boards, but how does the capacity change when we drill a hole in it? Say we make an elliptical hole with the major diameter being half of the beam's depth. Let's see what happens. Hopefully, to no one's surprise, the weakened 2x4 failed at a lower load of 1820 kilos in what appears to be a tensile rupture of the wood grains, most likely due to the high stress concentration at the tip of the hole. But what do you think would happen if I were to make the hole wider or drill additional holes, taking out even more material? At a first glance, you may think I'm further weakening the beam, but this time you would be surprised. Before I show you the experiment, let's step back and give some theoretical background. Instead of going deep into technicalities, we can reason in terms of the flow analogy. This compares the stress state with an equivalent fluid flow state. The basis for this method is the fact that solids and ideal fluids comprise a continuum that for special cases can be expressed in terms of a potential function governed by a variant of the Laplace equation. In fact, most continuum mechanics textbooks do tackle both stress and fluid flow problems, which further speaks to the similarity of these problems. The analogy is in the flow lines and velocity vectors, which correspond to stress lines and stress magnitudes in the mechanical problem. But again, this is for a very special fluid which has no viscosity, nor the flow has any vorticity. The theory describing this fluid is known as potential flow theory and is heavily used in the design of offshore platforms. Now, if we look at a unidimensional bar element loaded in tension, we expect to see parallel equidistant stress lines. The same bar with fluid flow through it has analogous fluid flow lines that look identical. If we introduce a cut or obstruct the flow at one side of the member, the flow lines would get squeezed, resulting in higher velocity at the tip of the cut and essentially no velocity at the base of the cut. Since velocity and the stress magnitude are analogous, by extension, we can claim that the stress magnitude is high at the tip of the cut and virtually zero at the base. This is quite intuitive, but it is also confirmed with this finite element model. Let's see what happens if the obstruction was elliptical. The flow lines get squeezed at the top of the ellipse, let's call that point A, indicating high horizontal velocity and hence high horizontal stress. At the point of the minor radius, point B, the flow comes to a stop and changes direction from horizontal to vertical, goes around the hole and remerges on the other side of the ellipse. And sure enough, looking at the stresses from a finite element solver, we see a horizontal normal stress of nearly zero around point B, since the fluid has to slow down to make the turn around the hole, resulting in a low horizontal velocity. At point A, the fluid speeds through the tip of the ellipse, resulting in a very high horizontal velocity and hence high horizontal stress. The reason why the velocity of the fluid is high at point A is because we have extended the streamlines of the fluid particles traveling near the middle of the beam, so that the particles have to speed up around the hole in order for continuity to be maintained. By continuity, I mean the amount of fluid entering the bar has to be the same as the amount of fluid exiting the bar, meaning the particles from different parts of the bar have to enter and exit at the same time, so that there is no fluid backing up inside the bar. So, the question now becomes, how can we reduce the length of the streamlines around the hole so that the particle does not need to speed up as much? Since lower velocity translates to lower stress, one answer is by filling in the hole, but that's kinda boring, so alternatively, we can also shape the hole in a way that provides a smooth path of the streamlines. This is very counterintuitive when thinking in terms of mechanical strength, since it indicates that removing material is supposed to make the element stronger. However, thinking in terms of a fluid flow, we can identify that the fluid should indeed flow more smoothly around the hole. So let's find out if that is the case. But while you're here, Don't forget to subscribe to the channel. This is a very easy way to help me out produce more content. Now back to the experiment. So instead of enlarging the hole, I just drilled additional holes on the sides, which should provide the same effect. The flow is notified of the abrupt change and it starts curving around the hole early on and therefore avoiding abrupt changes in the flow direction. Let's see how they perform under load. Note that the bearing plate is too small for this application, resulting in punching shear that essentially cuts through the grains. The load reached 1930 kilos before the bottom of the beam splintered. This is a 6% increase in capacity compared to the beam without relief holes. I find this result absolutely astonishing and very counterintuitive, but before concluding too much, I repeated the test 2 more times just to make sure that this 6% increase was not just a statistical luck. This time, I drilled a few additional smaller holes just to make sure a nice smooth transition in the streamlines is achieved. All of these samples were taken from the same 2x4, so in reality there shouldn't be too much variation between them, but I repeated the test anyway. The new samples achieved 2140 and 2010 kilos, confirming the effect of the relief holes. It is worth mentioning that the flow analogy works best for plates subjected to a uniform normal stress, whereas in our beam, the normal stress varies linearly and is also accompanied with shear stresses. But regardless, the flow analogy definitely holds some weight, as we illustrated with this experimental campaign. In summary, the unaltered 2x4 achieved a load of 2300 kilos and failed in what appears to be a shear failure. The whole beam, without relief holes, failed at 1820 kilos, while the whole beams with relief holes failed at 1930 kilos, 2010 kilos, and 2140 kilos. So, drilling relief holes provided a capacity increase of 6, 10, and 18%. Keep in mind that if holes are drilled at a wrong place, the structural integrity of the element can be severely hindered, so I do not recommend you providing relief holes unless consulted with a professional.